Well, hi there, gang. Now that you have mastered derivatives of exponential functions, we're going to move on to do derivatives of logarithmic functions. So specifically, logs that have base a, so that could be any base, and the specific natural log that has the base of e. So we'll find out how to do the derivatives of that. They're related to the derivatives of exponential functions. So just like you had 3 parts to do an exponential derivative, you'll have 3 parts to do a logarithmic derivative too. So let's get to it. If you have any logarithmic function, its derivative comes in the following 3 parts. So if the logarithm has base of a, so that could be any base, and then u is what would be in the log. And a lot of times there's the implication that there's parentheses here around whatever that u function is. All right, so part 1 is right there. That u immediately goes in the denominator. Okay, you've got 1 in the numerator right here, and then u goes in the denominator. Part 2, we need the natural log of a. That also goes in the denominator. So we've got a difference automatically with the exponential rule. The exponential rule took that exponential and then multiplied it by the logarithm. And here we see both those parts in the denominator. So u and ln a. And then part number 3 is to be expected. That's our chain rule here. All right, so the derivative of any logarithm works that way. So let's try that here with the natural log of u. Right, so part number 1, well, we start with a numerator of 1. We're going to put u down here because that was what the logarithm is of. Then we're going to put the natural log of the base, and in this case we're base e, and then we'll multiply by the chain rule, and the derivative of u is du dx. So we can clean that up because the natural log of e does have a value of 1, so the simplified version of that is 1 over u, and then times the chain rule, du dx. So that's how it works with a natural log. Let's try it with some other logarithms. Find the derivative of logarithm in the base of 4. Okay, so we'll start with y prime. And because it is a logarithmic derivative, we start with a fraction. And so into the denominator is going to go the u function, which is what's here in this parentheses. So I'll keep it in parentheses, 2x minus 1. Part number 2 is the natural log, and the natural log is applied of whatever the base is. In this case, the base is 4. And then we multiply it by the derivative, the chain rule of what was in the parentheses to begin with, which is 2. Now the rest is just cleanup. My numerator has a 2. I'm going to put my ln 4 in the front. And then I've got a 2x minus 1. Now the reason I put my ln 4 in the front is what we talked about yesterday about the number 4. The number 4 is a power. It's 2 squared. And remember that with logarithms, you can pull that power out to the front of your logarithm. So that's going to make my expression in the denominator have a 2 out front. So it'll be 2 ln 2 and then parentheses 2x minus 1. And what that allows me to do is reduce my numerator and denominator. And so my numerator is now 1. And then I have the natural log of 2 parentheses 2x minus 1. Okay, so the calculus was right away at the beginning, and then we are using our properties of algebra and our properties of logs to simplify. Let's keep going. We're going to use those same properties to simplify this before we do our derivative. So let me remind you that the 5x rad here, the rad 5x can be written using parentheses. So this could be written as the log base of 10 with parentheses around the 5x instead, and then you'd have a 1/2. And what that allows you to do, again, is apply that property of a logarithm where you can pull that power out to the front. So I haven't done any calculus yet. All I've done is some algebraic properties in the log base of 10. By doing that, that's going to make my calculus work a little easier. So my calculus work will be y prime is, and I just have that coefficient, that constant 1/2 sitting out there. And then my derivative is going to be 1 over, part number 1 is the 5x, part number 2 is the ln, and that's of the base of 10. And part number 3 is the chain rule of the 5x, which is 5. So that's the calculus part. Now we're ready to simplify that. And so my 5's will reduce. And what I'm left with is the expression 1 over, I've got a 2, I've got an x, and I've got an ln 10. And that's the expression of the derivative. And remember that that derivative can be used to find the slope along this original logarithmic base 10 curve. Okay, here's another one. Here's a chance for us to find the derivative, this time of a natural log. So we'll look right at f prime. 1 over, because I'm doing a logarithmic function. All right, part number 1, x squared minus 3x. Part number 2, natural log of the base, which is e. Part number 3, the derivative, which is 2x minus 3. And we'll simplify, knowing that the natural log of e is 1. And so I'll have 1 over, excuse me, not 1 over, I'll have 2x minus 3 over the quantity x squared minus 3x. Now it wouldn't hurt us to consider factoring the denominator, so I can take an x out, leaving me with x minus 3. It doesn't help me right now, like that doesn't reduce or anything, but having things in factored form in the long run tend to usually be a good idea because we'll be doing other things with derivatives in the future. So thinking about things as factors will prove to be useful. Okay, for this one, as I look at what's in the parentheses, I think there might be a better way for us to write that algebraically before we do calculus. So again, thinking of things algebraically, sometimes you do things algebraically after you've done the calculus, other times you do it before you do the calculus. Neither is, right or wrong. One often just tends to produce a cleaner answer than the other. So if you get stuck, if you've done calculus first and you're stuck on your algebra, why don't you just pivot, stop, go back, try some algebra first, and then try the calculus, or vice versa. So in this case, I am going to keep the parentheses, but I'm going to write it as x to the negative 1. And what that will allow me to do is to pull that negative 1 down to the front. And so the negative 1 becomes a coefficient of ln x. And then I can do y prime, just with the coefficient of negative 1 sitting in front of the regular rule for my logarithm. So my numerator will be 1, part 1 will be the x, part 2 will be the natural log of e, and part 3 will be the dx part, which simplifies to 1. So a couple things that can simplify to 1 here. This is 1, natural log of e is 1, and so y prime turns out to be a numerator of negative 1 and a denominator of x. Now what if we hadn't done algebra first? Okay, so let's just think of, in this format, what if we just did part 1, part 2, part 3, and we did it that way? So that would be 1 over. Part 1 would be 1 over x. Part 2 is still going to be the natural log of e. And part 3 is going to require the quotient rule for me, which will be x times 0 minus 1 times 1 over the quantity of x squared. So that just ends up to be messier because I've got a fraction under a fraction. I've got a quotient rule I have to deal with, and then comes a lot more complicated algebra. So that's why I'd recommend in this case doing the algebra at the beginning rather than the algebra at the end. Okay, for this last example, let's tackle looking at the normal line. So again, we always need to be thinking about our point and our slope. So remember, for the point, we're going to plug x equals 0 into f of x. And for our slope, we'll be plugging x equals 0 into f prime. So plugging into f of x first, that'll give me the natural log of 0 plus 4 plus e to the negative 3 times 0, or 1. So overall, that's natural log of 5. For f prime, I'm going to need 1 over. All right, part 1, x plus 4 plus e to the negative 3x. Part 2, ln e. Part 3, the derivative of what was in the parentheses. So that'll be the derivative of x is 1, or dx dx, which we can change to 1. The derivative of 4 is 0. And the derivative of e to the negative 3x we learned yesterday. That's part 1, e to the negative 3x, part 2, ln e, and part 3, negative 3. So let's clean all this up. This is 1. This is 1. This is 1. So let's see what we have. What is left in the numerator? Well, it looks like I have 1 plus, how about minus 3 e to the negative 3x. And the denominator is x plus 4 plus e to the negative 3x. Now, as much as I would like to, these e to the negative 3x's do not reduce each other. Why not? Well, one's attached to a 3 with a subtraction, and the other is attached to the 4 plus x with addition. So I can't reduce either of those, but I can plug in 0. So I'll have 1 minus 3 e to the 0 over 0 plus 4 e to the 0. So 1 minus 3 over 4. Negative 2 over 4. So negative 1/2 is my slope. Now to write my normal line, I'll use the point I found. So y minus the natural log of 5. The normal slope, if the tangent slope was negative 1/2, the normal slope is 2. And then x minus 0. And voila, we have our normal line. All right, I got it in under 15 minutes. So you can have the rest of the class time to get started on the derivatives of logarithms. And good luck with that. And we'll cover the combination of logarithms and exponentials in the final lesson of section 3.4. All right, see you later.